Good morning. Good morning, everyone. Welcome to today's Fight 2. My name is Xiangling Lu. I am from Department of Physics, National Taiwan Normal University. And first of all, I would like to introduce today's jury. The first jury is Professor Jiang Haibang. Give a big hand. The second jury is Professor Huang Xuming. And the third jury is Professor Lin Zhenxue. And the fourth jury is Professor Hu Huanyu. Thank you. Now I would like to ask the team leaders to introduce your team members. Please introduce your team members. Include three information. First, their name. Second, their grade. The third, their hobby. Please introduce your team members, their name, grade, and hobby. And let's start with the reporter, team leader. Could you introduce your team members, their name, grade, and hobby?
Hello, we're Team Tribute from Geisler High School, and I'm Sophia I'm second grade, and my hobby is to play violin. And she's Sophie Ye Jiayu, and she likes to play cello.
Cello.
And
What grade?
First grade, and he likes to code. And she's Wu Jane Wu. She likes to second grade. And she likes to sing.
Singing, wow, wonderful. So welcome to Fight 2. Thank you. And the opponent, Yuan AY13. The team leader, please introduce your team member, name, grade, and hobby. Thank you.
We're Yuan AY13. Yuan AY13. And my name is Yu Xiuxian. My hobby is drawing.
Drawing? Please stand up. Okay, introduce. Would you stand up? Stand up, please. We'd like to know you.
Okay. He is Chen Shu. His hobby is to watch anime.
Watch
Anime.
The grade?
We're all first grade.
First grade. Thank you.
This is Tobo Wei. His hobby is to investigate something about physics.
Oh, something about physics. Please make a note.
Okay. This is Wu Jiahai. His hobby is something about history.
History is great.
And then this is Wang Huahao. His hobby is to listen to music.
Listen music. So great. Welcome to Yuan AY13. So welcome. Now is the reviewer, Afar. The team leader, could you introduce your team members' name, grade, and hobby? Thank you.
Okay, and we're Team Abbas from Jinchen High School, and my name is Jane, and my hobby is to dancing and listen to music.
Dancing and listen to music.
Yeah, and she is Angel. Her hobby is playing volleyball.
Playing volleyball.
Yeah.
Great.
And she's cheerleading. His hobby is listening to music.
Listen to music. You have to make some friends here.
And his name is Sam.
Same.
His hobby is to hang out with his girlfriend.
Hang out your girlfriend. Oh my God, you are just a senior high school student.
And he's Mark. His hobby is to observing some physics like here.
Observing some physics. Okay, so
This investigate and and participate in this tournament because he's participated in this tournament for the third time. Yeah, he's in the third grade.
third grade. So the other are second grade.
We're second grade and he's also second grade.
Great.
Thank you.
Thank you. Welcome to our team. Welcome. Now we start to our stage 1. The opponent challenged the reporter for the problem. Opponent?
I'm the opponent. I want to challenge choosing character.
Which number?
16.
Number 16. Opponent challenged the reporter for the number 16. Choosing text. Reporter accept or reject this challenge?
Reject.
Reject. Reporter reject the challenge number 16. Could you write down here? Assistant. No, assistant.
Okay.
So, opponent would you challenge the reporter? Another problem?
13. Charge meter.
Number 13. Charger meter.
Reject.
Reject. Opponent rejected problem number 13. Opponent, would you challenge another problem?
Problem 4. Shooting rubber band.
Problem 4. Shooting rubber band. Reject. Okay. Number 4. Reject number 4.
2. Droplet microscope.
Number 2. Droplet microscope.
Reject.
Reject. Wow. 最后 the maximum reject problem are 5.
15. Let's go.
Opponents challenge the reported number 15. Wet scroll.
当拒绝题目到第5题后，则不可再继续拒绝题目。
好，对。Will you accept or reject problem number 15?
Reject.
Reject. 15. So the final. Now the opponent challenge your problem, you have to accept it.
不好意思，我稍微朗读一下。在整个初赛 PF 期间 ，reporter 可以拒绝至多5个题目，其中可拒绝3题不被扣分。当拒绝题目超过3题，每一题将扣 reporter 的积分权重 0.2， 且此扣分会沿用至该场与尔后所有初赛 PF 4。当拒绝题目到第5题后，则不可再继续拒绝题目。
好的，
完毕。
记得说，那个时候其实就有说少于5题的时候开始
有没有解禁的那个？现在题目只剩3题，有没有？
好，现在从曾经由 opponent 所讲述过的题目，也就是第5题开始解禁。所以现在第5题是可以选的。
opponent 讲过的题目可以开始解禁。
刚刚就要多了，现在3题而已。
对。
哦，刚刚就要先多了。哦。
对，刚刚就要有了。
OK。
现在只剩下3题啊，刚刚就要写题目上去。
你说在3题的时候。
先从 rocket 跟 roller trick 被解禁了，对吧？
哦。
Sorry， 但是好像
刚刚就要
重来。
所以现在先从3题那边重来吗？
对，必须重来，因为他们 们的决定会
你们会改变你的决定？
他们会改变。
好，所以现在可以再放去哪一题？
先把后面
那我们2跟15，
为什么不交？
是不是这样子？
没有，就是因为刚刚程序有问题。对，所以我们重来。
你就重来挑战。
不是。
不说完全重来。
所以
不用完全重来，这样就好。
对啊，从现在开始。
从现在开始。
好。
所以现在就可以解释了，不好意思，因为下一次
他们还有解释。
不要再
助教再看一下，这样可以吗？
这样子对。
正确吗
？280。
总共剩5。
对。现在是280、11跟11。
没有，他的 reject 只有3题。
哦，没错的哦。3题。所以他现在还可以 reject。是reject。
现在还有580，580。
还可以 reject 2题。好。可以好，那 opponent 现在继续 challenge 了。OK。Opponent, please challenge the reporter problem.
Problem 15. Let's go.
Problem 15. Okay, reject again.
这样多换，
助教说明一下。
这是这样子，他们来做。
那现在15是要是怎样？
这也太。
助教再说一次。
现在要解禁1题，所以现在解禁的是第5题。
解禁第5题，第5题放上去。助教确认一下，可以吗？正确吗？
是。
正确。
对，解禁第5题。
这可以吗？好。那 opponent, you have 5 problems available to challenge the reporter. So please select one. 11.
How many show?
你只能接受了。
accept.
Accept. The reporter accept the challenge. Problem number 11. Accept the number 11. Now the
不好意思，教授，那个现在按下去以后，他现在还有 challenge problems 要按，然后我不太晓得是什么情况，这是程序的问题。
怎么样？现在是？
对，我觉得程序我刚请别人拍。
我们现在就是 reporter 正方案5分钟准备啊。
对啊，我现在是进不到下个。
那是你的 computer 的问题。
确实。
那我来提醒好了，5分钟8点。And each team, please write down the name of the representative, please, on the blackboard.
方案错了。
然后你用谁？
你可以听，你要注意。The representative for the reporter is Su Rongxuan. Opponent representative name is Zhou Guowei. Reviewer. Wang Yanzhen. We have 3 minutes left. 2 minutes left.
我现在是等我一下，是 reject， 重看，15 reject， 然后它又跳回来变成
1 minute left.
accept，
注意你的计时可以了吗？
还不
你要不要找系办的
好，
技术人员来协助你？
回答一下。
不行哈，你那边有故障。
对，
那我来记好了。
谢谢。
And now the reporter give a presentation. You have 12 minutes, so I will be the timekeeper. Thank you.
Hello everyone, we're Tim Trudeau and I'm the reporter of the pumping straw selection. So the problem statement says that a simple water pump can be made using a straw shaped into a triangle, and so it's partially immersed in the water, and it will rotate around the vertical axis, and so the water may flow up to the straw. So investigate how the geometry affects on the pumping speed. And so we think that the key point of it is its velocity of the water and the geometry, like the parameters. And these are the parameters. So first it's the rotation, angular velocity, like how the straw, like the whole pump rotates. And second is the straws, the diameters of the straws and the side length of the straw and like how much it's immersed in the water. And the tilt angle, like how the angle of the two straws, and so it will cause the pumping speed, like its exist velocity and the maximum range. And so this is our experimental setup. So camera we use 240 FPS to like the slow motion to see how it rotates and how the water goes out. And the rulers so this is our main setup. And so we use power supply here, and it will connect to our motors and it will like the straw will like it is in the motor, and so we have the bucket and water supply, so to make sure that the water stays like the water height of the inner bucket stays the same. So this is our the straw we use, like how we make it, and so here's our theoretical qualitative theory. so we consider it's so the water at the higher position accelerates faster according to the equation. So we consider it the water stream was split into water droplets. So we have to consider it like the small water segment. So this is our quantitativity theory. So this is the small segments and F equals ma. And this is radial acceleration equals normal force and gravity. This is like an ideal condition. Now, so the ejection of the water, we use Python to simulate how will it be. So this is velocity. So however, there are some things we have to correct. So first is viscosity and so pressure difference. This is the we use Darcy-Weisberg equation, and so we calculate its Reynolds number, and it's bigger than 10,000. So we think that it's the turbulent flow. So we put it in the this equation, and then so we can get the FD, and FD which is on the FD in the Darcy-Weisberg equation, so we can get the pressure difference. And so if we count the viscosity, and it will be the velocity of the water in our field in our theory will be lower. And so then we consider the Bernoulli's law. And so if the faster the velocity is, the pressure difference will be bigger. So the Bernoulli's law, if we consider it, it will be the correction will be larger when the velocity is higher. So and then we consider the surface tension correction, and so the surface tension will pulse the water upwards. So it will be more easy to come out the straw, and the velocity of it will be faster. So if we consider the surface tension, it will be higher. The velocity will be higher. This is what we simulate like this. So concluding all these factors, we kind of set the effective gravity equals the gravity and what the viscosity will cause, and minus surface tension and Bernoulli's law. And then we consider air resistance, but it is too complicated to consider all of this. So at final we make it to 2. So this is, and this is our experimental verification. So we can, so if we measure the how far the water comes out, when it drops to the ground, how far is it from the original position, as we see at our experimental setup here. So we measure how it comes out, and we use ruler to measure. And so this is our experiment. We use slow motion to take videos of how it spins, so how it rotates, and then we put in new trackers to see how fast it rotates, its angular velocity. And then we measure the the distance the water dropped on the floor. And so we compare it with our theory. So first we discussed the effect of immersion depth. And this is like the theory said that they will be slightly different when it immerse in different height, and we concluded at larger depth will affect it's not really significant, but it will be higher velocity. And then so this is our experiment, and the grade is our confidence interval. And so this is we consider the effect of the straw diameters, and in our theory, so basically it's the surface tension is significant at smaller diameters. So at the theory we said, and so surface tension will pull the waters upward, so the velocity of it will be faster. So smaller diameter, higher velocity. And so this is the effect of the straw diameter. And the effect of the tilt angle. We measured two angles, 30 and 60, and 60. And in our theory, that said that so basically 30 is bigger than 60. And this is our data. And so we discussed the optimal tilt angle, and we use this equation, and it shows that there is an angle that can make the velocity faster, and it's 36.6. And so let's move on to our conclusion. So this is our theory, and we corrected with the viscosity, surface tension, air resistance, and Fermat's law. And so viscosity will cause smaller pumping speed, but although it's not really significant. And surface tension will cause larger pumping speed. Bernoulli's law will cause larger pumping speed, and air resistance will make the droplet slower. And if larger immersion depth will cause larger immersion height and higher rotating speed, and smaller diameter like the straw diameters, and the critical a specific tilt angle will cause larger viscosity velocity. Thank you.
Okay, thank you very much, Rongxuan. So give her a big hand. So now the opponent asks the question to the reporter. 2 minutes.
Okay. The opponent and ask first. For the pumping speed, you investigate the existing velocity, but not the mass flow rate of the pump. Why? I measure the physics velocity, but not the mass flow rate. The mass change by time. Why?
It's really hard to.
Okay, and the next. How do you define your H naught? H0.
H0.
Right.
So in our experiment, it's so you mean like this one? You mean like the of it?
No, H naught. H0. 13th stage. 13th. How can you say the blue line and the red line is not parallel? How can you explain that?
So I mean like here.
Right.
There's the condition like before the water doesn't go out of the straw and then the foam comes out. And so higher surface tension actually will make the flow of the water more easily to come out the straw. So it will first
Sorry, the time is up. The preparation of the opponent 3 minutes. Now the opponent, Guo Wei, takes the floor. Makes about 4 minutes.
Okay. I'll start my presentation. I'll summarize the report. And the reporter used a very variable of theory to try to explain their data, and we think it's very good, but there are some, I think, mistakes. And these are some texts of this problem. Accurate, reliable device for experience and complete explanation of the phenomenon and measure the mass flow rate. But the reporter measure the velocity and different variable parameters and a model of prediction. The reporter did that. Okay, and these are some pros and cons of reporters. sufficient data and accurate measurement, and the prediction of Bernoulli slope, viscosity, and air resistance and surface tension. But the reporter, I think, is lack of the phenomenon description and don't have enough parameters and a misusing of Bernoulli slope. Okay, let's go into our discussion.
So now is a discussion between the reporter opponent. Okay, ready?
Okay, we're going to the viscosity part. Right, and on the x plot is FD. FD.
What is it?
No.
This one?
Yeah.
It's like
And what's that for?
so if you use a turbulent, it depends on the flow parameters.
What's the value? What's the value of this? In this experiment, what's the value?
I'm not really sure.
Okay. Okay, let's come to the next part. Wait. Can you go into the Bernoulli flow? But you consider this Bernoulli flow. Okay. Why say no Bernoulli slope?
It means like if you don't consider Bernoulli slope.
And what is P1 and P2?
P1 is the pressure down, like the downward here.
How can you know the pressure downward?
So this is like because we assume that this is P1 and this is P2, and we discuss how would it affect.
So the P1 is bigger than P2, right?
Yeah.
So the half rho v squared plus rho g h must be negative, right?
I'm not sorry, what?
As P1 is bigger than P2, then the half rho v squared should be wait, how can you measure the P1 and P2? How can you figure it out?
We calculate it.
How can you calculate?
We assume that because we discussed like the thing we discussed is like the delta, the pressure difference between it. So we assume that P1 is 0.
Wait, what is tau? What is tau? Half rho v squared and rho v of tau squared. Where is tau? What? The even the unit is not right. If tau is torque, even the unit is not right.
It's the velocity, the exist velocity.
Oh, it is velocity. And when you calculate this velocity, tau is a point, right? I'll think that's a point. And where did you consider the V? You need the data of.
We need the data of R, and then we put it into the.
I think when you use when you create your circle model, you need the information of the position, right? So where? It's the central of the stroke, right?
Yeah.
But I don't think so. I think caused by the centrifugal force, the water should be flow out at the outmost point of the pump, right? So when you do the circle prediction, we think you shouldn't consider the point is on the central part.
Like, you think you shouldn't read that?
I think here. Okay.
So we think that.
Okay. Then go to the air resistance part. The air resistance formula says the series of the V is the force is proportional to V squared, right? Okay, then why you use this formula? Because I think this formula is for high speed situation, not low speed.
This one?
Right.
So we didn't consider it after all.
So
It's too complicated, and like as you said, it will like it doesn't fit in like slow angular velocity. So then we just discussed we just consider it at 2, like this, so that it'll fit the theory.
then why can you do this? Can Siri explain your experiment by this?
Yeah.
VT is
We found that it's too complicated to use this thing. So we figured out that it will be more fit the theory if we consider it as 2.
VT is about 2 meters per second, right? But I don't think so. If VT is equals to 2, and then you think the force is a constant, right? The force in different situations is a constant. You think that, right? But the delta V is per a single same size, same mass droplet. We think the I'm sorry, can I use the blackboard? Okay. What do you think is delta T equal to m delta V? I thought delta V. I thought you need the same delta T. So you can consider when the F is the same, the delta VD is the same. But I don't think so. I think then let's do another part. We want to ask the surface tangent part. Right. Yeah. Higher tangent, higher V. And how you consider your surface tangent T as 2 pi a gamma?
That is the equation of surface tension.
No, I think the 2 pi A is because the A is the radius of the stroke, right? You think the 2 pi A is the whole length of the stroke, right? Around.
Yeah.
But I don't think it would be a round. Be a circle, right?
Yeah.
A circle. How you can think your service tangent can be considered as a circle. A force act on this circle. How can you do that?
The straw is circle and the water.
The water contact the straw might not be circle, right? Can you go there? Makes sense. And this is true. I thought it might not be like this. The water there, water down, and it might be like this.
I see it. And yeah, it does, but you can't, like, it's too complicated to consider all its like all how it's like.
Hey, it seems like you just on that end. I want to take a look at the phi, which is the phi. Right. And I don't think your model fits, your theory fits, right?
Yeah. So
The y-axis, the bt, you don't have to compare between that, right?
you mean
Compare
this?
it, but no, the y-axis is the b tau, and the left side is the vent. It's shut down, the water shut it down, and did you compare them?
If you get the range and then you put it in the equation in my
Sorry, I
experiment.
want to actually find the question. And how can you consider the delta P of the Bernoulli equation? Because I don't think Bernoulli equation can be used like this.
No, this is like we discussed. We consider how it affects on the experiment. So.
Thank you. So now the opponent Bo-Wei summarize the discussion 1 minute. Please.
Okay, for the viscosity, I didn't really know. I asked what's the VT, the coefficient of the viscosity formula, but I don't think the reporter answered and for the Bernoulli's law of delta PPD, the pressure difference caused by the Bernoulli principle. The reporter also didn't give the great spherical answer. And okay, that's all. Thanks.
Thank you. Now the reviewers, Yan-Zhen asks questions to the reporter and opponent. 3 minutes. Please stand up.
First, I want to ask both the reporter and the opponent, does the laminar flow exist? Do you think it exists in the situation?
No, it's for the level flow.
It's okay.
Also, I think it doesn't exist because the ruler did consider the RE value.
Okay, so do you agree with that? B in will be equal to B out. There's a side difference, and there's the downward point is sucking the water up. So and the upper point is pumping out the water. So the speed between that, not the speed, the the downward speed is equal to the upward speed. Do you agree with that?
No, I don't. I think there will be different. Like the upward will be faster.
Then what's your opinion?
I think if the upward will be faster, then the shape shouldn't be wrong, right?
Shouldn't be wrong.
The shape of the water and the water surface shouldn't be a circle. Okay. Right.
And so, do you agree with that she used the variable slope to consider the theory?
No, I actually didn't agree with that because I thought canonical principle is not used like this because the reason why the principle is useful is the pressure differences is only force that will change the mechanics energy. But here I think the centrifugal force or possible act will act, right?
And I want to also ask about the way of calculating the distance. So you can drop on the backboard. The system from the top, you see the system. There's a triangle from the top that in my experiment, the flow will be like this. It's not a really circle. It's more like a 3D. You need to use 3D to analyze it. So you use it or you just this is so it's like this one too.
Sorry, time's up. The preparation of the reviewer, 2 minutes. Now the reviewer, Yanzhen, takes the floor, 4 minutes.
Honorable juries and fellow competitors, this is Jane, the reviewer from King Albert Shinton High School. And here's a summary of the report. For experimental part, she included the motor, and a ruler is also used to measure the coming speed. And the parameters they use is the angular velocity, tilt angles, and the diameter of the straws. And also a comparison between the theory and experiment is made. For the theoretical part, the centrifugal force is introduced in the theory model, and also a dirty whiplash is applied, and the viscosity Bernoulli's law is considered in it. For the recorder's performance, she has some strong points, like she has clear quantitative explanation for it, and also the diameter of the phenomenon is well presented. The programming simulation is also presented, and also a wide variety of theoretical model is involved, such as viscosity and surface tension. And for the weak point for her is a three-dimensional consideration. For a summary of the oppositions, the experimental part is the flow ratio measurement. He has discussed it. And also the theoretical part is the surface tension deviation, and the viscosity is also discussed, and the drag forces he also discussed. And for the opponent's performance, he has clear expression, and he pointed out the recorder's theoretical problem. And for the weak points, he didn't discuss the question X. And he didn't raise his own point. He just asked these questions, and he's over focusing on the parameters that are used in the recorder's theory. He didn't ask much about the experiment, and he should be more focused on the currency. Yeah. So for the discussion, the opponent asked the recorder the consideration of the positions that are used for calculation. In the recorder states that it's a middle part. And our opinion is that so there are some deviation in general. However, the model can be support the recorder statement, so it should be fine. And for the previous question, I first asked the opponent and reviewer, does the laminar flow exist? And they both disagree with that, and I agree with that because and I also asked about the downward B is equal to the upward B, and also they both say this is not correct. And the last one, I asked if it's, did the opponent agree with the Bernoulli's law of the report? And he says no. Thanks for listening.
Thank you. So now the concluding remarks of the reporter, Rochen, 2 minutes.
So when the opponent said that they think we should consider the reuse of this law, like it's not circle. We think that it does have slightly differences to our experiment, but it's too hard to measure it. So yeah, and then the reviewer asked us to use the 3D dimension, and we didn't measure it. It's too complicated, but we will do it. So, and then so about the Bernoulli's law, the water will be pulled out of the straw because of the pressure differences, and we just use it to fit, like to put in our experiment to correct it, not because like the opponent said, and so we think that it should put into our experiment theoretical model, and we think that the upper water goes faster. That's all. Thank you.
Thank you. Now the questions of the jury. So the opponent reviewer, please stand up. Questions from jury.
Can you explain?
Professor Gu.
explain more why the upper water can go faster than the lower one?
It's at like George. So here you see that this sink, the sink is proportional to R, and the upper, like the water at higher position will have like the bigger R. It will accelerate faster.
More questions from juries?
I'm also wondering, since water is liquid, then how do you measure this distance? Whether if I give you a drop of water, of course I know your instrument should be used, but I just wondering, how do you measure the precise distance? Because it is like this continuous input. So therefore, I'm just wondering how you decide the eventual distance. I can imagine that at different times, the distance should be different. So then, how do you determine the eventual value of your distance?
We average it.
Any more questions from the other three juries? Professor Nian?
The question for each of you, starting from the water. Do you think that when the angular speed will be high enough, then there will be a change for the air appear to the water drop? In other words, in the straw, there might be section of water contained by air starting.
Yeah, I agree with it, but in my experience, I didn't actually see the phenomenon. I think I'm not faster, like my angular velocity isn't that fast.
Thank you. Followed by
Same question.
the question is whether it may happen when the rotating is faster enough, then the water won't become continuous and interrupt by section of air.
It's not well because the diffuse static coordinate system on this related with the stroke, not on that. We can see the centrifugal force, right? I think it's proportional to the omega squared. So it will. I think it would be very big that the pressure of air won't act. Won't win the centrifugal force.
For the reverse view, in my consideration, I think the system, the water in the pipe is more like the laminar flow. So I think the situation won't happen as fast as air goes in.
Thank you.
Any questions from the other jury? If there is no more questions, please. So now it's the grading for the jury. Now the grade for the reporters. Please, the jury, please show your grade. Okay, 5, 4, 7, 6. 5, 4, 7, 6. And the grade for the opponent. 5, 7, 4, 7, 6. 5, 7, 4, 7, 6. And the grade for the reviewer. 5, 6, 5, 7, 8. 5, 6, 5, 7, 8. Right? Now we close the stage 1 and we will take a 10 minutes break. And please come back to the classroom after 10 minutes. Thank you.